All right, I think we're ready to go. So we'll be doing the optimization of reaction conditions. Last week you ran the reaction with the chlorobenzaldehyde. You actually started not with the ylide but with the phosphonium salt, reacted that with potassium hydroxide, so you converted it to the ylide, got a Wittig reaction, and got a mixture of products. We did do a wash with the ethanol water to try to remove the triphenylphosphine oxide. And when you look at your data, you'll probably find that we were only partially successful. There's probably still some present. But at this point, we're needing to identify which isomers are present and the relative amounts. And we're going to be using gas chromatography. It's quantitative. It will tell us the amounts that we have, but it does not identify the particular compounds. Mass spectrometry will help you identify the peaks as far as whether or not they are alkene or unreacted aldehyde, triphenylphosphine oxide, or something else. But it doesn't distinguish between the two isomers. So we won't know, we'll know we have this peak and this peak are both alkene, but we don't know one is cis and one is trans. And that's where the NMR comes in. We can use that to figure out the trans and cis ratio and find out which is the major isomer. And then we can look at the GC and we expect to see a similar ratio there. And so we can use that to identify it. Before we talk about that, just quickly with the report, same guidelines as before, nothing new here. Procedure, you've done all this. The one thing new with procedure is at the end you do have the summary statements and you have not done mass spectrometry before. So for the mass spectrometry, again we identify the technique, MS. We typically identify the medium that we use for obtaining it, a solvent for NMR or UV, salt plates typically for IR. In mass spectrometry, this is done in high vacuum. Okay, the sample is going into a system that's under very high vacuum, and so there is no medium. So all we have then are units, and M/E is the units. It stands for mass per charge. So if you have a peak at 210, then you have a mass of 210 with a charge of +1, potentially a mass of 420 with a charge of +2. But given the conditions that we use for ionizing, double ionizations are very unlikely. And then after that, you give the major peaks, so peak at 210, and then we identify what that fragment is. And you can either identify it by putting M+ representing the parent ion, or writing the fraction of that fragment, or you can do the parent ion and represent what's lost from it. And I'll talk a little bit more about that when we talk about the mass spectrum, and in particular the discussion for that. NMR, one other comment with that, you've seen all this before, but for NMR you now have two products. You've got the cis isomer and you've got the trans isomer, so you should have two data lines for the NMR. One for each. So you would simply put trans and then colon NMR and you give the peaks for the NMR. And then cis and then you do the same thing for it. In theory, you should be doing the same for the mass spectrum, but frankly, it's kind of pointless because the cis and trans have identical mass spectra. You'll have exactly the same data lines. There's no point in putting the same thing twice. If it actually distinguished between the two isomers, there'd be no need for the NMR. Okay. All right, calculations. Some of this is routine, limiting reactant, theoretical yield. Remember, you do have three reactants. You've got your base, you've got the salt, and the aldehyde, so you have to do limiting reactant for all three. And then theoretical yield of alkenes. But this time we're also going to be looking at a calculation of a crude yield for each isomer. So for example, if you weighed at the end of the procedure, if you weighed 0.814 grams, it means you had 0.84 grams of stuff, but it was not pure product. It might not even be pure alkenes. You could have alkenes plus aldehyde plus triphenylphosphine oxide. We want to know what part of that mass is specifically transalkene? What part of that mass is specifically cisalkene? And we don't care about the others, just the two alkenes. And so you'll need to calculate what portion of that is each isomer, and then calculate a percent yield for each isomer, and then also diastereomeric excess. And we'll go over each of those calculations as well. In fact, you need to do these before you leave today. You'll need to do those and then submit them. We'll go over those, and you can ask questions as you're working on that if you need to. Okay. So we've got basically three goals. One, of course, is to determine what products you have, whether you have the cis isomer, the trans isomer, or both. And we don't care about the other stuff. We'll just call it other stuff. And the mass spectrum and the NMR spectrum are what we use for that. We also want to determine the relative amounts of cis and trans. And so we'll need to use the mass spec to identify the alkene peaks, the NMR to identify the major isomer, so you know then in the GC, if the major isomer would be the bigger peak, and then use the GC to get the area percents so that you know the relative amounts. Okay. And then the third goal, the reason that you all had different conditions is to determine what the optimal conditions are for the synthesis. Which one gives the best results? And so that's the third thing that we'll be looking at. All right, so as far as the NMR spectrum goes, you've got something, or may have something that looks a lot like this. And the first step then will be to determine which peaks are the vinylic peaks, which one belong to the alkene hydrogens. And you've done this before with the first Wittig that we did. This is where you use that equation, the 5.25, plus the geminal, plus the cis, plus the trans effects of each of the substituents there. And so you'll do those calculations. And then once you have that for the two hydrogens on the trans and the two hydrogens on the cis, you'll see which peaks they match up with. And that will help you identify those. And then you can also determine which is the major and which is the minor. And of course, we want to confirm that cis-trans assignment. And for that, you will be using what? What'd you do before for cis and trans? Remember? Remember coupling constants? So for each peak, you will determine the coupling constant. So for example, if this is one of the isomers, you would simply take the difference between those two peaks, 5.8314 minus 5.799, I think that's an 8. Nope, that's a 6. So you would simply subtract these two numbers, multiply by 400. If you get a coupling constant somewhere between the range of about 8 to 13, it is a cis isomer. If it's somewhere between 14 and 18, it's the trans isomer. And if you get something much bigger than 18, you probably did your calculations wrong. For hydrogen coupling constants, I don't think you'll ever see something greater than 18. So, and just remember, it's always, even though we have, the notation is often written HA minus HB, we're not doing A minus B, we're doing the two here. That designation simply means the coupling between those two hydrogens. Okay. And so you'll calculate that and confirm, and hopefully what you get, if the coupling constant here is cis, the chemical shift should match one of the cis. If this has a trans coupling constant, then that chemical shift should match the trans calculation you did for that as well. Okay. And when you are in your discussion and conclusion, since again we have two isomers, you need to have two tables. And in those tables, you would identify definitely the vinylic peaks, which you've identified with the chemical shifts and the coupling constants, but you should also identify the other peaks for that particular compound. So for example, we have here a quartet. It is in that 3 to 4.5 range where we typically see alkoxy. So that tells us this is an OCH. If we look at integrations, 1.95 to 1.08. It's a 1:2 ratio. So that tells us it's an OCH2. Splitting's a quartet. So what's it bonded to? How many neighbors do we get if we have 4 peaks? 3 neighbors, so it's bonded to a methyl group. So we know that this is bonded to a CH3. And in fact, if we come down here, we can see we have integration of 3. And it is a triplet. Integration tells us it's CH3. Triplet tells us that it is bonded to something with 2 neighbors. So bonded to a methylene. So these are bonded to each other. So you should be able to identify that. And that, would, of course, would be the ethyl ester portion. And in fact, we've got another small triplet and quartet. And again, if you look at the ratio 0.7 to 0.39, roughly a 1:2. So this would be vinylic for the minor isomer, and this is the ethoxy, again, for the minor isomer. And you should be able to identify those. Now, depending on your spectrum, you may get a spectrum that looks a lot like this, in which case, again, the other peaks that were down there, you'll probably be able to identify them, although maybe not. If you did not leave your sample on the rotary evaporator long enough, you may have hexane peaks that overlap your triplet for that ethoxy, in which case you may not see that. In particular, if you have a lot of noise in the aromatics, this one has aldehyde. I don't have the aldehyde peak out here, but that's out here as well. And we also have a lot of other aromatic stuff, probably from triphenylphosphine oxide. When you have that, you probably will not see the aromatic peaks for these for the minor isomer. Integration here is 0.25 relative to this one. And so the aromatic peaks will be twice that, since it's a 2-to-1 ratio. So you expect peaks about 0.5. That's going to be lost in here. If you can't find them, don't worry about it. Just leave it out of the table. The major isomer, you should be able to find all the peaks. The minor isomer, you probably will not be able to find all the peaks. If you can, great. If not, don't worry about it. So for the minor isomer, you may not get all the assignments. And again, that depends on the peaks. And you can identify some of these. For example, if you look at the aromatic peak, or excuse me, the aldehyde peak out around 10 ppm, if you set that to 1, look for the peaks in the aromatic region that are integrating to 2, and you should be able to identify the aromatic. And then when you set one of these to 1, you can look which ones integrate to 2 and match that. Although if you have a lot of impurities, the integrations may be a little messy anyway, so it may be a little problematic. And if that's the issue, don't worry about it. This is the data you have, and you work with what you've got. And there's not anything we can do about it. We just accept the fact that we're not going to find all the peaks, and that's okay. Any questions about the NMR? And if you have specific ones with your NMR spectrum, when we're working on calculations to submit that, you can bring those up as well. All right, so let's talk about gas chromatography. This should be fairly familiar. You did a few of these in Organic 1. Basically, we have a sample that was injected into an injection port. This is kept very hot, so it immediately vaporized. We're constantly blowing a carrier gas through. For the GCMS, we're using helium, and it goes through the capillary column, and the peaks separate. You've seen this with the Organic 1. Basically, samples will vaporize. As long as they're in the vapor state, they're moving through that column, but the column is kept somewhat cool, still hot enough so that we get vaporization, but we'll also get the condensing down into a liquid. And as long as it's in the liquid state, it stays there and does not move. Once it vaporizes, it gets carried again. And because the different components have different volatilities, they spend more or less time in the vapor state, and so they go through at different rates and they get separated. And eventually they come out to the detector, and you get a chromatogram. Looks like this. You also get a report usually with it, lists the retention times. And what's important here is area percents. This is the relative amounts of each one. The problem we have when we look at this is it does not give us any information about what these peaks are. Chromatography separates, and it is quantitative. It tells us how much of each thing we have, but it does not tell us what these are. And so we really don't have any way of determining which of these are alkenes, let alone which is the cis isomer or which is the trans isomer. And so we have this then coupled to mass spectrometry. So when it's coming out the other end, the gas chromatographs we have in the organic labs have an FID, a flame ionization detector. Basically, it burns it and looks at the ions that are formed during the combustion, and it gets relative amounts. But we can also make our detector a mass spectrometer. So as it exits that column, it goes into the mass spectrum. We have this little diagram, sort of a cartoon picture of what it looks like. And basically, the column is going right into the ion source. This ionizes a sample that comes in. We have some charged metal plates, so when you have a charged species, when you have an ion, it has a positive charge. If we put a positive potential on that metal plate, it pushes it out into this thing called a quadrupole filter. And it actually is 4 metal poles. But we can control the charges, the potential that's on these different poles, and tune it so that based on the AC and DC voltages we're applying, we can have it filter out a particular mass. So if we set it to 210, only ions that have a mass of 210 will come out and go down to the detector. Anything else will either go off resonance and impact on the rods, or it'll come out at the end and go off in an angle. And so it never hits the detector. So if we have it tuned to 210 and the detector starts detecting ions, we know we have something coming through that has a mass of 210. And the detector is also quantitative. It can tell us how much we're getting, how many ions. And so we can then tune it to a different mass and look at that. Are we getting ions coming through? And the usual way that it's run is called scan mode. And we will tell it scan from 50 AMU to maybe 400 or 500, 800, depending on what mass range you expect. And so if it's sitting at 50, it's looking, are there ions? Yes or no? Move over to 51, and then looks and then moves over again. And the path from the ion source to the detector is short enough, and the fragments, the ions are moving fast enough, we can scan a range of about 50 to 400 about 3 times a second. So we don't have to dwell at any one mass, but we can then scan, and that's how we get the mass spectrum. Okay. So let's talk a little bit about what's happening when that goes in. Sample comes out of the gas chromatograph, goes into the ion source. It's ionized, and so we get a molecule, or now an ion. In this case, this is what's called the parent ion. This is the original molecule as it came in. It's ionized. And if we have our spectrometer set to, or the quadrupole filter set to 210, we'll be getting hits telling us there's something coming in that has a mass of 210. And so we know that we have a parent ion there with 210. But ions tend not to be very stable. And so these can break up. If it breaks where that bond, that little red mark is across that bond, if that bond, that carbon-oxygen bond breaks, we end up with 2 pieces. One has a mass of 65, and it will be charged. The other piece is not going to have a charge on it. It will be a neutral radical. This is going to get sucked out in the vacuum. But this one, because it's charged, it's pushed out into the quadrupole filter and then directed to the detector when the detector is set to 65. Or excuse me, the quadrupole filter is programmed to 165. When it's there, again, the detector will say something's coming through. It can measure the amount. But we now know we've got something that has a mass of 165 on it. Of course, when that thing breaks, it could go the other direction, where this is the neutral radical, and the ethoxy group is the one that has the charge. And there, now we have a fragment that has a mass of 45. That's what goes into the detector, so we would see a peak in the mass spectrum at 45 as well. Could also break at the other side of that oxygen. When that happens, we get this. Of course, now something strange has happened here. This oxygen does not have a hydrogen on it. Where'd that hydrogen come from? In fact, this is a CH3, not a CH2. What happened? Anybody remember this from lecture? Pretty sure you would have gone over it with when you were doing mass spectrometry. This is the McLafferty rearrangement. You see this when you have something with a double bond here, and the rest of this molecule, the mechanism is up there. I don't think I have a pointer down here. But we have that chain where we have a total of 6 atoms in there, with that hydrogen being one of them. The oxygen could be something else. It could be a nitrogen, could be a carbon. We would still see the McLafferty. But that hydrogen from the terminal methyl group is transferred over to the oxygen. So really, it went up to this oxygen. I've rotated this to flip it over, make it look like the normal carboxylic acid. But it's that transfer, that rearrangement, that gives this and the ethylene group. Okay. So this is referred to as the McLafferty. But again, we now have an ion that has a mass of 82 on it. And so we would see that in the mass spectrum as well. So sample goes in, it's ionized. We should see a parent ion, but that will often break up into other pieces, and so we can see those different fragments. And we use that to try to identify what's coming out. So you can use that then to identify the compound in the mass spectrum. But how do we associate a particular mass spectrum with a particular peak in the chromatogram? If you look up here, and this is pretty tiny print, I apologize for that, but that tells you which scan number it is. But the important thing is retention time here. I think I have them set so that all of yours, the retention time here should match what's written up there. The default setting is for it to report the mass spectrum in minutes and seconds. It would have 5:27, which means 5 minutes and 27 seconds. Retention times on the chromatogram are reported not as minutes and seconds, but as minutes and fractions of a minute. So 5 minutes and 27 seconds is just shy of 5.5 minutes. 5.45 minutes is also just shy of 5.5 minutes. I think yours are probably set right. They do not have, for example, this one is written as 5:27. If it's that, then it's minutes and seconds. But the retention time here will tell you which peak you're looking at in the chromatogram. And that's how you associate particular ones. Okay. All right, so how do we interpret a mass spectrum? First thing we usually look for is the parent ion. We'll also try to identify common ions and lost fragments. So typically the peak with the highest mass is our parent ion. So this is the mass of the molecule that's coming in, and that's referred to as the parent ion. And then we can also look at common ions. Now this one, I've got something a little bizarre written here. The mass at 111, if you work with halogenated aromatics, that would probably be a common ion for you, but if you don't, this would not be a common ion for most people. Typically, when we talk about common ions, we're looking at masses like 15, which represent the methyl cation, or 29, which is the ethyl, or 43, which would be either propyl or isopropyl. Since they're isomers, they have the same mass. Another common one that we saw when we were looking at that would be 45, which is the OCH2CH3. These are things that are fairly common, that are seen a lot in mass spectrometry, just because we happen to have either alkyl chains 1, 2, 3 carbons, or the ethoxide and methoxide as well. The 31 would be fairly common, especially if you're dealing with methyl ethers or methyl esters. And one other that should be fairly familiar, 77. Remember that one? Does that ring bells for anyone? Back beginning of the semester. 77 is the mass of the phenyl cation. So the C6H5. So 77 would be that one. This one doesn't have any of those common ones, so I just picked a chlorophenyl, which again is not common unless you're dealing in that area. The other thing we look for is lost fragments. So we look at the parent ion and what has been lost to give the other peaks. So for example, we have a peak here at 182. So if we look at the difference in mass between 210 and 182, it's a difference of 28. And we would think then, what has a mass of 28? The two things come to mind. One of them is the diazo group, and N2. 2 nitrogen atoms have a mass of 28, but since we didn't have anything with diazo in our reaction, that's unlikely. The other one would be a CH2CH2. So when you have that, this would be evidence typically of a McLafferty rearrangement, indicating that you have commonly an ethyl ester or something related to that structure. Okay. If we go to the peak at 165, we look again, and we always start with the parent ion and then the difference in mass there. This is a difference of 45. Again, this is a mass for a common ion, and that is the ethoxy group. And so that indicates that whatever we have, it lost an OCH2CH3. So ethyl ether or ethyl ester would be the common sources there. But that's how we typically do this. And when we look at the differences, we always go from the parent ion and only rarely go from a fragment to another one. Typically, we only see a single fragmentation. It is possible that it will break, we'll get this fragment, and then this one will break again, and we get what's called a double fragmentation. Usually, though, those are rare enough that they're very small peaks. So if you are trying to identify peaks, look first at drawing your structure, breaking the different bonds, and seeing what the masses are. If you can't identify it that way, then you might look at, well, what if I break this bond and this bond? You know, what's the piece that we have? So double fragmentation should only be looked at when nothing else is giving you the mass you're looking at. All right. So one other thing to consider here is that we have our parent ion, and then we have another peak, 2 mass units higher, that's about the third the size. And in fact, we see it here at 182. We have an M plus 2. At 165, we have this tall peak, and again, we have 2 mass units higher. We have a second peak that's a third the size of this one. Does anyone remember what that is? That's the sign that we have chlorine. It's important to remember when you were dealing with mass spectrometry that what's going into the mass spectrometer are single molecules. And a single molecule will have either a chlorine that has a mass of 35 or a mass of 37. The masses we see on the periodic table are average masses. So chlorine, we've got 75% of chlorine atoms are chlorine 35. And 25% are chlorine 37. If you average that together, you get the 35.5. When you look at your molecule and you try to add up the molecular weight by adding up the masses of each of the atoms, you'll get a mass of actually 210.5, not 210 exactly, but that's because we're looking at an average mass for that, not single molecule masses. In fact, bromine would be a little trickier still. The mass we get there, 79.9, there is no rounds very close to 80, there is no bromine 80. It's either bromine 79 or bromine 81. And so you would actually get two peaks in your mass spectrum. If we had bromine, we'd get an M and an M+2 that are roughly equal size. But if you simply use the molecular weight on the periodic table to calculate the mass of something containing bromine, it would never match your masses on the chromatogram because you're using a mass of 80, but they're really 79 and 81. You'd have peaks one above and one below what you're calculating. It's important to remember that we're actually dealing with single molecules, and we have one isotope or the other. And that's why we get this is chlorine 35. These are the molecules that had chlorine 37 on it. Likewise here, these would be the fragments that came from a massive, or a chlorine 35, and these smaller ones are the ones that came from a parent ion that had a chlorine 37 on it. But this is useful in that when we see that pattern, we know we have a molecule that contains chlorine, and also we can look at it and say, well, this fragment has chlorine, this fragment has chlorine, this one does not. There is no peak at 104 that's a third the size of that. So whatever this is, it does not have chlorine on it. It's lost chlorine. And given that it's not just 35 less, sometimes you'll actually see that. You'll see 210 and then 35 less than that, which would be, 165, I think. Yeah, 165, you would have another peak. Oh, actually, this could be, yeah. So this actually has a mass would be equivalent of the loss of chlorine, but we know because we have this other peak here that it was not the loss of chlorine itself. Okay. But anyway, actually, I think I did my math wrong. It would be 175, but same point. In fact, we do have a tiny 175 from the loss of chlorine. But whatever this is, it's lost chlorine, and it looks like this is a double fragmentation that's lost something else as well. Okay. But yeah, that can be useful for determining that we do have chlorine in our product. All right, when you're discussing the mass spectrum, you do need to have a table. It says for each product, cancel that. You need to have a table listing the masses and fragments. Again, you're going to get exactly the same table for the cis as you would for the trans, so there's no point in putting it in twice. One table is sufficient. And you'll have then two columns, one with the masses or from the peaks, and the other one identifying the fragment. And as I said, you can do this either of two ways. You can show the actual molecule or the ion that you have, and these should all have charges. So you can put the ion and draw out the structure, put a charge on it. You can also write it out in a sort of a longhand fashion. For that parent ion, you could write Cl, phenyl, CH, CH, CO2, and you could even abbreviate this ET. And you could write it out that way. Of course, put your positive charge on there, but you could write it out that way. Or you could put, for this, you could also just say M+. M+ is that because that's the parent ion. And so you could do either one. Typically, when chemists are filling this out, they're either writing what's easiest or they're highlighting something that's important about that molecule. So if we lost the OET, again, you could write this out. Like this. And because we lost, this is something that has lost the ethoxy group. So this would be the 165. Or you could write it M+ minus the ethoxy group. Either one of these is acceptable. Whichever one you find more convenient, you can write that out. Okay, so either method works. And you should do the major peaks. This one, 111, such a small peak, it's really not necessary. But you should go with the major peaks that are in the mass spectrum. Smaller peaks, you can ignore them. In fact, the small peaks are often hard to identify because they may be from double fragmentations or rearrangements or other weird things going on. So just the biggest peaks. Let's see, so, and then underneath that, of course, you'll have a discussion, identify the peaks. So you'll say there was a peak at 210. This corresponds to the parent ion. Peak at 182 represents a loss of ethylene from a Clafferty rearrangement, just a simple statement for each one of the peaks that's present. And you should probably also mention the fact that there is an M and an M+2 peak indicating the presence of chlorine. And that should cover the mass spectrum. Gas chromatogram, again, you'll have a table listing the retention times, the mass percent, and the identification of at least the alkenes. You may not be able to identify all the peaks. A couple of them that should be fairly straightforward might be the triphenylphosphine oxide and aldehyde if you have those. You can simply look at the masses for those. In fact, as far as the discussion for the mass spectrum, you do not need to discuss any of the mass spectra other than the alkenes. I don't need any discussion about the aldehyde or the triphenylphosphine oxide. You can ignore those. Those are other things. All we're trying to do is identify the product or the products we're interested in. So with the gas chromatogram, you list the retention times of the peaks and then identify the compounds. And so in the discussion, you're going to talk about how you made those identifications as well, which would be, these two peaks were identified by the mass spectra as the alkenes, and NMR indicated the major isomer is the trans, therefore the larger peak is the trans, and just how you made that identification. And the other peaks, you don't need to identify them. For the aldehyde and triphenylphosphine oxide, if you identify those, you can simply state peak at 4.2 minutes, whatever the retention time is, had a mass of 140, which equals the mass of chlorobenzaldehyde, and no further mention is needed for that. Okay. All right, calculations. Crude yield of trans isomer, crude yield of cis isomer, crude yield of other by difference. We'll go over these. As I mentioned, at the end of the experiment, you weighed something out and you got a mass. But as you know from your chromatograms, they're not pure. You've got more than two peaks. You definitely have more than just two alkenes. And so you need to determine what portion of that is actually alkenes and what portion is specifically transalkene versus cis. And so this is where the mass percent from the chromatogram comes in. So for example, if we identify this peak at 5.46 minutes as say the trans isomer, you would go to area percent. This is telling us that 57.3% of the material that you had at the end was actually trans isomer. So you would simply take the mass that you weighed. Again, assuming that it was 0.814 grams, you would simply multiply by 57%, and then that means you had 0.467 grams of actual transalkene. And you would do the same thing for the cis isomer. Look at the chromatogram, find out what the mass percent is for the cis. And again, you would have here 0.814. You're simply multiplying it by the mass percent for the cis to find out how many grams of cis was present in that product. And those are the crude yields. And we call it a crude yield, indicating that it hasn't been purified. Usually when you say percent yield, it's implied that it's been purified. If we say crude yield, we're indicating that it's not purified, but we still know the exact amount that's present, even though we haven't purified it and separated it from everything else. And that's why we put that little crude in front of it, just to indicate this is still part of a mixture, but we have quantified how much is there. Okay. Crude yield of other, we're going to just do that by difference. So take the total mass, again, the 0.814, subtract out the mass of trans, 0.467, mass of cis, whatever we calculated, and anything else then is just other stuff. It may be a mixture of aldehyde and triphenylphosphine oxide and possibly other things. We don't care what those are. We're just labeling that as other stuff. Okay. And then percent yield is just actual over theoretical, but in this case, our actual yield is 0.467. So for actual yield up here, you would have 0.467 and divide it by whatever your theoretical is. And then, so for example there, if we had a theoretical yield of 0.885, and I just made up that number, but suppose that if that was our theoretical, we would divide it, and we have a 52.8% crude yield of trans isomer. All right, final thing is diastereomeric excess. This is just a measure of how efficient the synthesis was in terms of making one isomer over the other. And for that, we simply take the difference between the two isomers and divide that by the sum of the two isomers. So if we have exactly equal amounts, the DE, or diastereomeric excess, would be 0, meaning there was no selectivity. If we have all major isomer and none of the minor, then we'd have, this would be equal to this. We'd have, mass, again, 0.467 minus 0, 0.467 plus 0. We'd get 100%. 100% DE means it was completely selective. So the higher the DE, the greater the selectivity. The lower the selectivity. And so if you get equal amounts, you get a DE of 0. Okay. So this is just a measure of selectivity. All right. Any questions about these? All right, we'll talk a little bit more about what's going on with in particular, the optimization portion. And then I'll put the calculations back up and we can start working on those. This is a drug called nirmatrelvir. It is an antiviral that's present in Paxlovid, which is the drug that's currently used to treat COVID-19. This drug is, if you get COVID and they decide to treat you with this, you get 300 milligrams twice a day for 5 days. Total dosage, 3 grams. You guys could probably make this. You need to be told the synthesis, but if you are given the reagents, I don't think there are any techniques that you guys don't know. If we gave you enough starting material, you could make 3 grams of this. The issue is the government put in an order to buy 10 million doses, which means the company, which I believe is Pfizer, has to make 30 million grams. How do you make 30 million grams of something? Basically 66,000 pounds. That's a lot of stuff. And the bench chemist, the person that made this and then sent it in for testing, would have been doing reactions on the scale that you were doing. Fairly small scale until they had some tests indicating this might be useful. And then they have to do scale-up. The guy that does the scale-up is the process chemist. And the process chemist may use the same synthetic method that the bench chemist used, but he or she may also decide there's steps in here I don't want to have to deal with. For example, if it's giving off a lot of heat, it may be difficult to contain that. If you've got a small container, you have a fairly large surface area to volume, it's easy to cool. Very large container, it may be easy to cool the outsides, but that heat is concentrating on the inside and you're not getting that heat transfer quickly enough. That may actually be a problem. And so they may decide that it's too hard to cool it, or maybe impossible to cool it, or you're dealing with reagents that are dangerous that they'd rather not have. So the process chemist may actually change that, or just the yields may not have been very good. The bench chemist is trying to make lots of different compounds for testing as quickly as possible. And then the process chemist's like, okay, we want to make this as cheap as we can. And they also have to source the materials. This is the synthesis that's used. This is an amino acid, N-protected and ester protected there, and it's got this pyrrolidine group on it. That they can buy this in multi-ton quantities isn't too surprising, but a couple of steps, they convert it to the amide there. This one I was actually surprised. I wouldn't have thought you could buy tons of this stuff, but apparently it's available. That's one source. One thing you have to consider is, can I get enough of the starting material? If not, I have to go to a different starting material. But convert it to these two, put them together, and then dehydrate, convert it to nitrile there, and you get the final drug. So again, the question is, how do you make this? And the other thing to consider when you are working on that scale, or this is enprofylline. This is an older synthesis. It's used as a bronchodilator, or at least was at one point. But notice the scale for this is a single reaction. Every time they ran this reaction, they would start with 475 kilograms. That's just shy of 1,000 pounds of propylamine. They would convert it to the urea. They add the acetonitrile group to this. And at this point, they have in their reactor, in their round bottom flask, so to speak, a bit over almost 2¼ tons of material. And then finish it. Yield has gone down a bit, but still 828 kilos. You're still talking just shy of 2,000 pounds of material for each run. So this is the scale that things are done on. This is a picture from a plant that this is not related to either of the other two compounds, but you can see the size of the reactor. We've got a person here, so you can see the size of their flasks that they're working in. And of course, pipes are convenient if you can dissolve things and pipe it in so that you don't have to carry it. Sometimes you just open the top and you carry bags, 50-pound bags of stuff, and dump them in. And I've actually heard of some where they buy it in bags that dissolve in the solvent. And they don't even have to cut the bags open. You throw it in, the bag dissolves, and your reagent's dispersed. But this is the scale that you're doing when you're trying to produce large quantities of material. In fact, I didn't watch much of Breaking Bad, but if you're familiar with that, there was a scene where the guy was working, I think it was in somebody's basement. It was actually developed for that, but you saw some of the huge reactors they were using for that. This is the kind of stuff that's actually done industrially. And when you're working at that scale, even small improvements in yield can be significant. But the process chemist, in addition to looking at different synthesis, might look at different solvents. Does it work better in a polar solvent, in alcohol, or less polar in ether, or maybe non-polar like hexane? What is the reaction time? If you don't go long enough, of course, you might have low yield. Go longer. If you go too long, it's possible you're just wasting time, that nothing's happening, and you could be cleaning that reactor out and getting it ready for another batch. Or it's possible your compound is even going to decompose, that you may get a steady increase in yield up to a point, and if you continue heating beyond that, that suddenly it starts going down as your product undergoes some kind of reaction and decomposes. And so solvents, reaction times, temperatures, all those matter, and those are things the chemist looks at. And those are specifically the things that you've looked at. And so you need to determine what are the optimal conditions. And in this case, we're looking specifically for the transalkene. Okay? Not total alkene, so you can think of yourself as being the manager of a plant, and you're deciding what's the best set of conditions to make this compound. Choose well. Everybody here gets to work. They get bonuses, and everyone likes you. Choose poorly. Plant goes out of business, and everybody gets laid off, and all your colleagues here are upset with you because we're getting close to Christmas, and they suddenly lost their jobs. So you want to choose well, choose wisely. And how you define optimal conditions is up to you, but do tell me what you're looking at. You can consider cost of solvent. You don't have to. Reaction time, of course, if it's a shorter reaction time, means you can clean things up and get to the next, repeating it again. You're probably not going to run all 66,000 pounds of material in one reaction. It may be multiple ones, so you'll want that reactor to be able to be recycled. Something to keep in mind, about reaction times. Who had 15 minutes for a reaction time? You did. Were you out in and out in 15 minutes? No. It takes time to set up, takes time to do the workup. So 15 minutes does not mean, oh, I get to do the reaction twice in the time the person doing 30 minutes does. You still have the other stuff, but it does still save time, and it can be a consideration. Yield of product, selectivity, and you may look at a couple things. For example, you may have two reactions that give similar yield. One's higher selectivity, or one may have very little byproduct, and therefore there's less cleanup to do. So you can look at those other factors to say what it is that you're looking at when you define optimal conditions. And I won't second guess what you're choosing. Where I will have issues is if you say, well, I chose ethanol 15 minutes at reflux because it gave the highest yield. And I go and look at the data and it is not the highest yield. Or just as bad, I chose the ethanol 15 minutes at reflux because it gave the highest yield. And I look at the data, and sure enough, it gave the highest yield, 127%. Yields greater than 127 or greater than 100% are a problem. So think about what you're looking at with the data. Remember, this is student data. People may make mistakes. They may have misweighed something. May have been a mistake in calculations. So think about what you're looking at and make sure it makes sense. You don't need to redo calculations in the table, but do look at that. And when you're entering stuff in the data table, it asks for first alkene and second alkene, not major versus minor, because it might be one set of conditions may give the cis as the major, a different set of conditions may give trans. So you'll put those in. But I think I've seen where people have transposed that. Maybe they actually had the data they entered. But 3 people have ethanol for room temperature 15 minutes. The first isomer is somewhere in the range of 10 to 20%. Second isomer is in the range of 90 to 80%. And then there's one person that has them flipped. In that case, I'm suspecting the person that has them flipped probably did put them in wrong. But typically, we don't try to change their data. We simply look at it and say, this looks like bad data, and cross it out. Same thing if someone gets greater than 100%. Just cross that one out and look at the other trials. But as long as your optimal conditions fit what's the data, and it makes sense, you're good with that. So justify your choice.